I'll get started. Once I get up here. Dearly Father, we thank you for this day again. I thank you for this class, and just ask that you'd guide our steps today, help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. So, we are covering systems of equations again, but now we have a new way to look at it in terms of matrices, right? So let's do that. First of all, let me fix this. I seem to have lost my eraser shirt. I don't know where I put it. It's very sad. I have been lowered to using paper towels. It just doesn't have the same, it's not as good. So I talked a fair amount about different ways to look at matrix multiplication last time, right? But there's another one that I should mention, which is if we have a matrix column product, we can look at it as a linear combination of the column. So here's a proposition. If A is a M by N matrix, and X is an Rn vector, then AX is actually equal to x1 times column 1 of A plus x2 times column 2 of A plus plus x sub n times column n of A, right? Now, I don't know if we've talked about what's a linear combination in here yet, have we? No. What do I mean by linear combination? So, definition, if C1, C2, all the way out through Cn are, let's say, real numbers, and V1 through Vn are objects, all right, which can be added. Then C1, come on, the sum I equals 1 to n of Ci Vi, which is just a shorthand for this, right? Is a linear combination of the V1 through Vn. Now, for the most part, we're thinking about linear combinations of vectors. But you could talk about a linear combination of like a matrix also, all right? So this is a linear. Let me just to make a couple of comments here. So any V in Rn we can write as what? We can say V is what? V1 all the way out through Vn, right? Or we can write it as V1 E1 plus plus Vn En, right? Where those are the standard basis. So any vector can be written as a linear combination. Well, you're garbage too. I got some new blue markers in here, somewhere in here. I'm going to find one. You'll see. Oh yeah, there we go. So any vector is a linear combination, all right, of the standard basis. If we have any matrix A in, say, R m by n, right? We can write that A as, a linear combination of its components times Eij. Now here, this Eij is called the matrix unit. The way it works is it's Kronecker delta Ik, Kronecker delta JL. Just to make it a specific thing, it's 1 if I equals to K, and J equals to L, and it's 0 otherwise. So I don't know if these matter too much to us in here, but just for your edification, these are the matrix units. For example, a 2 by 2 matrix. If I have A is like A11, A12, A21, A22, yeah? I can rewrite that as A11 times 1, 0, 0, 0 plus A12, 0, 1, 0, 0 plus A21, 0, 0, 1, 0 plus A22, 0, 0, 0, 1. These 2 by 2 matrices I just wrote, these are the matrix units. So this is E11, this is E12, E21, and finally E22. So we could build any matrix from like a linear combination of those kinds of basic matrices, all right? So here's some important examples of linear combinations is my only point, all right? So one of the problems we want to understand today is the problem of when is it possible to write one vector as a linear combination of other vectors. This is the so-called spanning problem. So let me write the problem out here. So here's the problem. Given, let's say V, an n vector, and let's say W1 through Wk, also n vectors, is it possible to find V in the span of these W's? Now let me tell you what is the span of the W's? What does that mean? What is the span of the vectors W1 through Wk? What's that? What's that about? That simply is the set of all possible linear combinations of the W's. Set of all possible linear combinations of the W's. So like explicitly, this is the sum I equals 1 to k of Ci Wi, such that the Ci are real numbers, right? In other words, let me rewrite this problem again one more time. We're trying to solve V is equal to C1W1 plus dot 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 plus CKWK. Can we solve this? Can we select C1 through CK for this? All right, can we do it? So I'm going to first show you an example with some specific numbers in it, and we'll work through it, okay? So example 1, we'll do a like a 4-dimensional example. Oh, what am I saying? 4-dimensional? 3? How about 3? 3 is enough. So is V in the span? I guess I better make up a V, huh? Let's say V is equal to 1, 2, 3. Is 1, 2, 3 in the span of 1, 0, 1 and 0, 1, 1? Question mark. All right. So here my W1 is this guy, right? And my W2 is that guy. The equation system, the equation I'm trying to solve is 1, 2, 3 equals to C1 times 1, 0, 1 plus C2 times 0, 1, 1. So what is that though? I mean, all right, so we've got what? We've got C1, and then first component C1. Second component is C2. The third component is C1 plus C2, right? If I just add these vectors. So look what I'm trying to solve. I'm trying to solve 1 equals to, I'm trying to solve, let me write it the other way around. C1 equals to 1, C2 equals to 2, and C1 plus C2 equal to 3, right? Where are those equations coming from? I'm saying the first one has to match the first one, the second one has to match the second one, and of course the third one also has to match, right? That's how we can get equality of these. So I need these three equations. It looks like the answer is yes. So, indeed. Yeah. C1 equals 1, C2 equals 2, C1 plus C2 is 3, so we solved the equations, yay. And yes, 1, 2, 3 is equal to 1, 0, 1 plus 0, 1, 1. And so, indeed, affirmative, 1, 2, 3 is in the span. All right? I wasn't trying to make it this easy. Like, usually you actually have to work to solve these equations, right? They're not usually like that. All right, so example 2. We can ask is 1, 2, 2, 4 in the span of 1, 1, 1, 1 and 1, 2, 3, 0, right? Yep.
Are all of the C's necessarily scalars?
Yes, the C's are scalars by construction here. I can't multiply vectors, so yeah. My current notation, the C's are scalars, yeah. Like I said, Ci is an element of the reals in the black there. All right, so we're trying to solve C1 times the vector 1, 1, 1, 1 plus C2 times the vector 1, 2, 3, 0 equals to 1, 2, 2, 4. So a better way to look at this problem is like I just wrote it, because then we can use the proposition I started this class with, right? I can repackage this simply as 1, 1, 1, 1, 1, 2, 3, 0 times the vector C1, C2 equals to 1, 1, 2, 2, 4, right? And then how should we solve that problem? We should look at the augmented coefficient matrix, right? That's what we should do. So the augmented coefficient matrix for this problem is simply 1, 1, 1, 1, 1, 2, 3, 0. My inhomogeneous term, 1, 2, 2, 4, right? So my opening move would be to do like row 2 minus row 1, row 3 minus row 1, row 4 minus row 1. which gives me 1, 0, 0, 0. Row 1 doesn't have anything happen to it, right? All right, so 2 minus 1, 1. 3 minus 1, 2. 0 minus 1, minus 1. Let's see here. 1. 2 minus 1 is 1. 4 minus 1 is 3. All right? We don't need to go any further, right? At this point, tell me what these equations mean. Like, what do these equations tell you? This one says that C2 is equal to 1. This one says that 2C2 is equal to 1. So C2 is equal to 1/2, right? We can't have both. We can't have C2 as both 1 1/2, right? Which means that the system of equations is inconsistent. So inconsistent, right? Thus, 1, 2, 2, 4 is not an element of the span of these vectors 1, 1, 1, 1 and 1, 2, 3, 0, right? So the question of spanning isn't that complicated, really. You already know how to do it, right? You just set up a system of equations and you try to solve it. But it turns out there's a far more beautiful way of answering these kinds of questions in terms of something called the column correspondence property. So I'd like to try to explain that to you. But in order to explain the column correspondence property to you, we need to take a little bit of a detour and talk about something called an elementary matrix. All right? What's an elementary matrix? We almost stumbled upon the idea last class, actually. So the way what an elementary matrix is simply this. You take the identity matrix, all right, take the identity matrix, and you do a row operation to it. So let's try this out. And then we'll see the significance of an elementary matrix as we do that. So let's do the, let's see here. We'll start with, yeah.
So since it's inconsistent, then one, okay.
Thank you, yes. I said it, but then I wrote the opposite. My apologies, yes. Yeah, no, you're not crazy. I just, yeah. Not an element, all right. I should give this thing a name so I don't have to keep writing it, I should have called it like Bob or something. 1, 2, 2, 4, not an element of Bob. Anyway, too late. Lessons learned. So suppose we take the 3 by 3 identity. This guy, right? And let's try different things. Like, let's try row 1 and 2 swap. Let's try a row 3 plus row 2. And let's also try like a 2 row 2. All right, so if we do row 1, row 2 swap, we get 0, 1, 0, 1, 0, 0, 0, 0, 1, right? This one gives us 1, 0, 0. If I add row 2 to row 3, I get what? Like that, right? And if I do 2 row 2, I get this, right? And let's call these, we'll call this E, 1, 2 flipperoo, and this will be E, I'll call this E row 3 plus row 2, I guess. It will be my name for it. And this will be E 2 row 2. These are stupid names, but they're the names I've given them. So what happens if I take the flipperoo one here, and I multiply it by a 3 by 3 matrix. I want to take a generic 3 by 3 matrix, so let's call it A, B, C, D, E, F, G, H, I. There we go. And what happens if I take the next one, and I multiply it by my generic A, B, C, D, E, F, G, H, I matrix? What do I get? And what happens if I take my other one? That was a 1, right? Sorry. And I multiply by my A, B, C, D, E, F, G, H, I matrix. What happens? Do these multiplications. How do they work out? So, if I call this matrix, well, okay, let me just do the multiplication. So what happens here is you get D, E, F in the top row, and you get A, B, C in the second row. And the G, H, I, it stays unharmed over there, down there. This one, the first 2 rows are unphased, but when you calculate the third row, you get, let's see here, D plus G, E plus H, and F plus I. All right? And this one here, the third one, the first row is unphased, the last row is unphased, unchanged, but the middle row, it gets multiplied by 2. So you got yourself a 2D, 2E, 2F. And this illustrates a theorem. Whatever we do to the identity matrix, right? If we do an elementary row operation to the identity matrix, all right? And we call that matrix E. Then E times A does the same row operation to A that we did to the elementary matrix. In other words, theorem, A going to, some row operation R is equal to E times A, where E is simply equal to I row operation. If that notation makes sense to you. We take the identity matrix, we do that row operation, that defines E, okay? E times A does the same row operation. The more to the point, every elementary row operation can be understood as a multiplication by a matrix. All right? So we haven't talked about invertible matrices in here yet, have we? No, we have not. But actually, all of these elementary matrices are what are called invertible. Because they can be undone. How do you undo an elementary row operation? You just do the opposite, right? Like, this is its own inverse, If I take 1, 2, and I flip 1, 2 again, I'm back where I started, right? And it's not an accident that if you multiplied 0, 1, 0, 1, 0, 0, 0, 0, 1 by itself, what do you get? We get 1, 0, 1. Whoa. I copied down the wrong matrix, didn't I? I'm like, this isn't working out for me at all. I was trying to do this one. I'm sorry, guys. I'll get it eventually. I was trying to do the first one. Like, this is not working out. That's that one, right? Yes. If you multiply that matrix by itself, we get this. That's 0, 0, 0, 1, right? That's the 3 by 3 identity matrix, right? So what this shows you is that E1 switcheroo 2 times E1 switcheroo 2 is the identity matrix. So here's a definition that I should probably give to you. If there exists B, let me write it more, sorry guys. If A is a square matrix, all right? And there exists B, a square matrix, all right, such that A times B is equal to the identity, and B times A is equal to the identity. Here we're talking about n by n identity, of course. Then B is equal to the inverse matrix of A. We say B is the inverse of A. We write A inverse equals to B, okay? So like this is a kind of funny matrix. Example, this calculation right here means that what? This calculation simply means that E1 switch around 2 inverse is, well, E switcheroo 2. It's its own inverse as it happens. This could happen. Now it turns out that the other two elementary matrices I have on this board, they're also invertible, but I'd have to work harder. Can you guys tell me what would the inverse matrix of E2R2 be? What if I did E2R2 times E1/2R2? Would that do it? So we've got like 1, 0, 0, 0, 2, 0, 0, 0, 1 times what? 1, 0, 0, 0, 1/2, 0, 0, 0, 1. Indeed, if you multiply these, you get the 3 by 3 identity matrix. So what this little calculation I just did in red shows you is that the inverse of this matrix is the same thing but with a 1/2 in the middle spot. Because if I multiply these two matrices, I get the identity matrix, which is like the number 1. All right? So it's usually way more complicated to calculate the inverse of a matrix, and we'll get back to that another day. All right? That's not my purpose today. I just wanted to illustrate this is the definition, and this is what an invertible matrix is. It's a matrix that you can undo the matrix multiplication by multiplying by the inverse. Just like 1/3 times 3 cancels out and gives you 1, right? Same kind of idea, but for matrices. My larger point is because we can undo any row operation, we can also count on all of these kind of elementary matrices being invertible. All right? So you notice here that I have tried to draw your attention to the fact that matrix multiplication, like matrix column multiplication, can be understood as a problem of linear combinations, right? So another way we can look at a system of linear equations is a question of spanning. Actually, every system of linear equations we can understand as a question about spanning. You're like, wait, what? What do you mean? Well, let's talk about it. Suppose I have m equations and n unknowns, right? So I've got, I can write that as a matrix problem. That's supposed to be unknowns. So as a matrix problem, that just looks like AX equals to B. where this is, this is of course shorthand for what? A11, A1N, AM1. I think I wrote this out last time, right? Remember that we talked about the coefficient matrix. So this is the coefficient matrix for the system, remember? This is the inhomogeneous term. And here's my vector of unknowns I'd like to find. So in the spanning problems, we were just looking at the x's were replaced with c's, but their role is the same, right? So if if you want, I can change the x to a c for the sake of this discussion to make it like more transparent. Let me do that. If instead of x we put c here, what would that look like? I'd have C1 through Cn, right? What is this, though? This is C1 times column 1 of A, right? Plus all the way out to Cn, column n of A, equals to B. What is this question? This is the question. This has solution, right? Only if what? B is an element of what? The span of the columns of A. So if we want to answer the question of whether or not a given vector is in the span of the other vectors, we simply assemble the coefficient matrix by just gluing together the spanning vectors and making the question, the vector of, we're trying to see if it's in the span, we make that the inhomogeneous column, and we row reduce, and that's that. That's the spanning question. All right. But check this out. If the reduced row echelon form of A with B, right, is equal to E times A with B, well, then that is also equal to EA times EB. Now here, I'm envisioning E is equal to like EK all the way out into E3 times E2 times E1. It's a product of elementary matrices. See, because if you think about the process of row reduction, we achieved it by doing row operation after row operation after row operation, right? Every one of those row operations I can implement by multiplying by a corresponding elementary matrix. So I have this formula, right? And as we'll discuss in more depth some other lecture, the product of invertible matrices is invertible. Important to know. All right, so if I suppose for a second that B is in the span, right? Let's suppose that this is actually happening for us for a given matrix A. And let's suppose that E is as advertised below. What happens when I multiply the boxed equation by E? What does that give me? I'd have what? I'd have C1 times E times column 1 of A, right? Plus plus Cn E times column n of A, right? Equals to EB. But also notice that if I was to say that this matrix here was R, so R was equal to EA, I could also write that as E times column 1 of A times E times column 2 of A dot E times column N of A by the column by column multiplication rule. So what I'm trying to argue is simply that the jth column of R there is actually equal to E times the jth column of A. As such, I can simplify this and say, well, really what I have is C1 times column 1 of R plus plus Cn times column N of R is equal to EB. Now that might not look like much to you, but what that means, let me put that in, let me write this as a sentence. So any linear combination seen amongst columns of A, yielding B, must also be seen amongst columns of RURF of A, B, with respect to last column there. See if I can. All right. Soprano is lively today. All right. All right. So here's a example. Where am I? Example. I suppose this was probably example 3, and this is probably example 4. I suppose. Example 5. Let us decide if 1, 2, 3, 4, and 4. Let me make that a 1, 2, 2, 1, 2, 2, 0. Make our life easier. Well, I don't know how much easier it is. I'll do all 4s in this one. 4, 4, 4, 4 are in the span of, let me say, 1, 1, 1, 2, and 0, 0, 1, 1. And let me change my answer just a little bit. Give me a second here. I'm going to change that out for 1, 1, 2, 3. All right. So I want to show you how to answer this question using what's called the column correspondence property. All right? So here we go. What I do is I take the given spanning vectors and I put them first. 1, 1, 1, 2. All right? 0, 0, 1, 1. Then I'm going to put these guys, which are playing the role of B, next. 1, 2, 2, 0, 1, 1, 2, 3. Now, let's do row reduction, right? So you guys know how to do that, right? So let's do it. All right, so let's see here. First up, I've got 1, 0, 1, 1. Nothing changes there. I'm going to have zeros here. 0, 1, 1, because when I subtract, all right, so 1, 0, 1, 1, and subtracting twice, minus 2, 1, I believe. And then I'll do row 4 minus row 3. Minus a 3. 0. All right, let me clean things up. Final move here. So I've got 1, 0, 0, 0, 0, 1, 0, 0, 1 and 1, 1 and 0, and oh yeah, thank you. Oh, I'm sorry, I got to do a better job here. 3. My bad. I'm sorry. Just a second, guys. I got to step back. So I've oh, fine.
The first two are 1, 1 already.
Yeah, let me. I'll do 2 steps rather than 1. My brain's not working at the moment. I'm sorry, guys. So 0, 0, 1, 0. I'll use this 3 to clear out that. That just gives me, and then I'll rescale it to 1. All right. And there's a 0 here, so nothing happens to these. And then finally, you guys double check me once I get my finish and move in here. All right, let me just make my partition red every time, just to. Are we okay?
How did the top row go from 1, 0, 1, 1 to 1, 0, 0, 1?
Because I divide this by minus, I mean, if you like, I can add, I mean, here's the, if you want, this is row 3 minus 1/3, or plus 1/3, row 4, row 2 plus 1/3, row 4, row 1 plus 1/3, row 4.
Okay.
Yeah. And then, of course, well, anyway, can I erase that? Because that's not entirely accurate either, because I did a bunch of things at once in that step, okay? Admittedly. But anyway, all right. So what does the column correspondence property say? The column correspondence property simply says that any pattern amongst the columns of a matrix will still be present in every single row equivalent matrix. A row equivalent matrix is simply the matrix that you're given with an elementary row operation done on it, or several of them. Now, this may not sound like much, but it's actually everything, because if you look at the reduced row echelon form, right, this guy, and so this, this was essentially, we put W1, W2, V1, V2, all right? That was this matrix. So this is these are the trying to see if these are in the span, right? And these are the spanning vectors. So you put your spanning vectors first, because those are what's available to build V1 and V2 with. All right. So here's my, and then I'm tired of calling. I'm going to call this matrix A, for lack of imagination. And so this is RURF. Maybe I shouldn't call it A. Maybe I should call it M. I'll call it M. I feel better about that. All right. If we look at the reduced to echelon form of M, right, and may I call this as column 1 is R1, R2, R2, R3, R4 for like I'm calling this matrix R. So like column 1, column 2, column 3, column 4. It should be immediately obvious that R4 is equal to R1 plus R2, right? And if you go back and you look at every one of these matrices in between here and there, it was also true for that. Column 1 plus column 2 was column 4. Column 1 plus column 2 was column 4. Column 1 plus column 2 was column 4. And finally, the one we're actually interested in, column 1 plus column 2 is column 4, because what that means is that W1 plus W2 is equal to, well, V2. So in other words, V2 is in the span of those vectors, right? Hooray. What did I not do? What's the difference between what I just did versus what I did at the start of class? I didn't even write down C1 and C2, did I? I didn't have to write down equations, right? That's the beauty of the column correspondence property, is you can just do row reduction on the appropriate matrix and read from that linear dependence amongst the given vectors. This is sneaky, but it's not that complicated. And once you know it, you can smash a great variety of problems with it. Notice that, on the other hand, it is also manifest from this calculation that the third column, R3, is not in the span of the first two, right? If we look at this column, third column, there is no possible way of building it from the first two. Yeah? Here's another example. Suppose you're given that the reduced to echelon form of a matrix that has V1, V2, V3, and V4, and it works out to 1, 0, 0, 0, 0, 0, 0, 0, and then maybe we've got, I'll put a 2 here, 0, 1, 0, 0, and then 3, 4, 1, 0, right? And I tell you that V1 happens to be 6, 7, 6, 7. And I happen to also tell you that V3 is equal to 1, 1, 1, 1. All right? So I'm telling you two of the, and let me give this matrix a name. I will call it A. So here's the question. Find A. So we're given the first column, 6, 7, 6, 7, right? And we're given the third column, 1, 1, 1, 1. What do the second and the fourth columns have to be? So the column correspondence property, see here, we have if I call this again column 1, column 2, column 3, column 4, you can see that column 2, R2, is what? How does it relate to column 1? It's twice. Yeah, it's twice column 1 in the row-reduced matrix, right? And so the column correspondence property, which I call CCP, says the same pattern must be present in the original matrix. So that gives us 12, 14, 12, 14. How about the fourth column? Can you guys tell me how that goes?
3, 4, 1, 0.
Yeah, how about this one? Oh, man. I meant to put a 0 here. So you guys are justifiably confused. Let's put a 0 there. Then everything is right in the world. My question makes sense. I'm sorry, guys. It has been a strangely long day for me today. I don't know why, but... okay, so with that, what can you tell me? Row 4 is what? I mean, listen to me, row 4. Column 4 is equal to what? It's equal to? How about 3? We need 3 times column 1. 3 times column 1, right? 3 of these. And then 4 column 3s.
I think you would also, if you did that, you get the same thing.
Oh, you're just saying column 1 plus column 2 is column 4? Yeah, that's very good, very good. But I'm sorry, there's part of a deeper...
Is that supposed to be column 2, or I mean row 2, not 3? You have 4 are 3, is that supposed to be a 2 right here?
no, I meant 3,
Oh, okay.
because I'm using this one
Oh, okay.
to get that.
Okay.
And I'm using this to get that. But you're right, I could have used the 2, but I don't.
Okay.
But anyway, so doing that, 18 plus 4 is 22, right? 21 plus 4 is 25. 18 plus 1 is 22. And finally, 21 plus 4 is 25. Okay, so there you go. That's the matrix. And we could check it with the website, right? You can put that in there, do the row reduction, see if you don't get back where I claim we started. This is the column correspondence property. If you try to attack problems that are based on knowing this without knowing this, they're impossible. So you need to understand what I'm saying about the column correspondence. I'm not saying much. I'm just saying that any pattern that you can see in the row reduced matrix must also be present in every other row equivalent matrix, in particular on the starting one that you're most interested in. My other comment to you is that we can always use the pivot columns to build the non-pivot columns. See this? The pivot columns were columns 1 and 3. I can build every non-pivot columns, namely 2 and 4, using a linear combination of the pivot columns. And if you think about the pattern of the row reduction, this is always possible. It's always possible to build any column in the matrix as a linear combination of the pivot columns. That's how it works. Any questions? Oh, I forgot to hand out the handy dandy attendance sheet. If you could, I feel like that was from earlier this week, so that would have been, what was it? Was it the 28th? Was it the, I can't remember. 26th was Tuesday, so today's the 28th, is that right?
Yeah.
All right, cool. All right, let us take a gander at the notes here for a bit. Come on, computer. Wake up. I didn't want to open up the wrong linear notes, right? You guys want the 221 notes, am I right? Not the 321? Yes. That would probably be best. Let's see here. Here we go. What did I just do? Did I just turn did I just turn it off? Oh man. Well, there you go. That's an illustration of my day right there. Okay, so I have been, I think we're past this stuff, right? So we're in chapter 3 here. And of course we started with, here you guys won't go to sleep, right? All right. So I start by just saying we can set it up as, take the system, we can rewrite it as a matrix times a column vector, right? Like we saw last time. That's the first idea. Then once we have that, we can talk about the solution set. Here's a notation for it. The solution set corresponding to that augmented coefficient matrix is like all vectors such that AX equals to B. Now, and then what I do in these notes is I develop some examples to show you patterns. And if I tried to write those examples out here in class, we'd spend the whole time and we still wouldn't get to the pattern. So let's look at them together. So that's a system. We found the solution. This is just recapping. We found the solution in the previous chapter using row reduction. And what that means then is if I take this matrix times, that particular vector, 83, 11/30ths, and 5/6, and multiply it by that vector, I get 170. That's what it means. To solve a system is to find a vector that when we multiply the coefficient matrix by the vector, we get the homogeneous term. Another way to look at it, as I've been explaining to you, is that 170 is a linear combination of this column, and that column. In particular, this 170 is actually 83/30ths times that, plus 11/30ths times that, plus 5/6 times that. Now don't make me work out the arithmetic, but that's true. That's what happens. And so like another example, if we had 2 equations and 3 unknowns, it would look like this. Okay, great. Who cares? I have the, so I don't, let's get past these. These examples are boring. They're just illustrating the fact that we can go from a scalar system to a matrix system, all right? So I hope that that's starting to be boring to you. Maybe boring's the wrong word. I hope it's starting to be not challenging, right? It shouldn't be challenging to go from this to that, yeah? Now it is challenging to go from this to that, right? That requires computation. Some of you are where you need to be on that. Some of you still got work to do. This always happens. That's okay. There's still time to fix that if you don't have it down yet.